Good morning, good afternoon, good evening, good wherever you are, and welcome to this SNIA Cloud Storage Technologies presentation on the influence of IoT on data strategy. For those of you who have not attended one of these presentations before, just a quick overview of the interface. There's a couple of things you'll be able to do. One is make the screen much larger than the little slot that you're probably viewing through at the moment. There's actually, you can enlarge it to full screen. And sometimes on slides that have a large amount of detail, it helps to be able to make it bigger so that you can actually read that detail. The second thing is that there is a mechanism for you to tell us how well we're doing and to vote on and give us a score for what you think of this presentation, along with your comments, which are always useful. A score of 1 is, I'd rather be doing anything else but this. And a score of 5 is excellent. This is the kind of thing we want. More, please. Any comments you may have as well, please do so. We're very grateful. We receive them very gratefully. The other thing you'll find is the ability to download this presentation. We're using the attachment and links feature. If you find that, you'll be able to click on it and get a downloaded copy of this presentation for your use. So, today I, Alex McDonald, am joined by Glyn Bowden of HPE, who's the Chief Architect of the AI and Data Science Practice. Good afternoon, Glyn.
Hi, Alex. Hi, everyone.
And Eric Hibbard, who's the co-chair of the American Bar Association SciTech Law IoT Committee, which is a terrific thing, because that means we were able to do all the legal stuff. Hello, Eric.
Good morning, and I am not a lawyer.
I-A-N-A-L. I am not a lawyer, and I do not play one on TV. Yes, okay. So that's us. That's your. I'm just simply going to direct the presentation this morning, or this afternoon, or this evening, wherever you are. And Glyn and Eric are going to be doing the majority of the chat. You also have the ability, by the way, as we go through this, to ask questions of us. If you want to ask a question, please do so, and I'll make sure that the speakers get round to answering it, should we have the time available. If not, we'll be putting them all in a blog at the end of the presentation, and I'll give you the link to that when we leave. So there's just a quick legal notice here. The presentation is copyrighted by SNIA, and basically the bit at the bottom, which is the key bit, is that there are no warranties, and if there's anything you do based on this presentation, and the thing you do it to breaks into 2 parts, I'm afraid both of them are yours. Although we're not lawyers, we're not actually going to accept any instruction from your lawyers either. So basically our copyright, and nothing that's in this presentation has a warranty associated with it. So who is SNIA? SNIA is the Storage Networking Industry Association. We're a group of 185 industry-leading organizations, household names, that have come together to promote storage and networking in a cooperative fashion. We've got something like 2,000 active contributing members doing things like presentations like this, and also developing standards for software and hardware that allow interoperability between our members' products. And we've also got around 50,000 IT end users and storage pros worldwide, of which you are a few today joining us on this presentation. So welcome. What we do is the CSTI, the Cloud Storage Technologies Initiative within SNIA, is very much to do with cloud storage and technologies. There's a surprise. The name is actually quite descriptive. But what we're trying to do is educate you on technologies that we think are of interest, and up-and-coming technologies that you're currently using, just to try and educate and make sure that people understand what it is we do as an industry. So we support and promote things like, for instance, OpenStack and Kubernetes. We've done several presentations on those, object storage, and those are just a few examples of the kind of technologies we'll talk about. And today's presentation is obviously on IoT. We also try and understand hyperscaler requirements and incorporate them into our standards and programs. And we collaborate with other industry associations, of which there are plenty, but I think SNIA, from the storage perspective, is one of the most important. So that's what we do as the Cloud Storage Technologies Initiative. So here's our agenda for today. And without further ado, I'm going to hand it over to Glyn Bowden, who's going to start the process of describing what is IoT and he will introduce Eric to talk about some of the security issues as we progress through this presentation. Please remember, you can always ask a question, and I'll make sure that Glyn or Eric get around to answering it before the end of the presentation. Thank you. Glyn, take it away.
Thanks, Alex. So our goal today is really to talk about IoT, but in the context of storage. So we will start off with a brief level setting of what is IoT, and that's not to, my expectation isn't that nobody has ever heard of IoT, and so I'm explaining from the ground up. It's really just to set the bar as to this is the way we interpret IoT and the things we are thinking about that are relevant to this presentation. So we only have the kind of 45 minutes, if you like, so it's a relatively short time to cover what is a vast topic. So we're keeping it simple so that we can talk about it in the context of the data that flows through it and the storage applications that get applied to it. We'll then have a look at a bit of a comparison between a traditional application, and by the traditional I mean the type of thing you'd normally find in a data center, you'd normally access through traditional means within your organizations, how they behave differently to what an IoT application, how that might behave in the type of data profiling you'll see from both of those, and where they converge and where they differ. And obviously then we want to talk about data 3 times apparently, and 1 in capitals, just to make it really clear. There's a lot of volume of data, and we're going to go on to make that point as to why that's a key thing, and really sort of drive home the point that the volume is the thing that matters here. Eric will then step in and talk a bit about the security of IoT, so securing devices, security of the data as it flows through the system, and some of the things that are happening in that space. And then I'll sum up really with just talking about the end-to-end flow of IoT data. So summarizing what we've already heard through most of the previous talk, but just giving it a bit of a polish, if you like, and making sure that we kind of portray where that data now lives, how it flows through the system in a visual way, hopefully to kind of round things out. And then we'll just summarize by just saying all the things I've just said again at the end. So let's dive in. So what is IoT? So firstly, IoT, Internet of Things. That's the first question I always get asked by my non-technical friends when I start using acronyms that they've never heard of. So IoT, Internet of Things, what is it? It's essentially the connections of all of the devices that live at the edge. So it's a bunch of sensors, it's a bunch of smart devices, it could be things in your home, it could be industrial IoT where it's things on large manufacturing equipment, it could be things like CCTV, scales, even toilets. And if anyone has a smart toilet, why would you have one? Anyway, so it's driven really by the plethora of personal devices that's exploded in the last sort of 10 to 15 years since the invention of the smartphone originally. We've all got something smart on us now. We're all carrying it around. It's generating data the whole time, and that data has to generally go somewhere. And if it's going somewhere, you can pretty much guarantee somebody's making some money off that data that you're sending out. So they care about capturing it, they care about keeping it, they care about processing it. We now have watches. I'm wearing one right now. You can't see me, but I'm wearing an Apple Watch right now. Other watches do exist. What it means is that the devices are becoming so personal that it's not something we necessarily have to carry around and actively think about turning on to use. It's something that passively sits there, absorbing data from our environment, absorbing data from around us, and transmitting it back somewhere else. It could be to the phone, it could be to a data center somewhere. But it's becoming part of what we are, rather than something that we have to actively go to. Of course, we have smart cars. And what I mean by that is the data that's coming from a car now. It used to be that you take the car to a garage to get it fixed, and somebody would take some of the bits out, and you can tell I'm not a mechanic at this point, put it back together again in hopefully a configuration that means you can drive off. Now, the first thing that happens when you drive your car into the garage is they plug it into a laptop and download some diagnostics. What's happening more and more is the car is sending those telemetry and diagnostics back to a data center anyway. If you've got certain brands of car, you'll have applications where you can do things like unlock the doors and turn the engine and heating on and off. All of that is going via a data center that's also capturing the telemetry from your car. So the car has become an edge device. It's a thing on the internet now. And as I mentioned, toilets, I don't want to dwell on that too much. As I said, if you've got one, well done. Then, of course, there's industrial IoT or industrial devices. Largely, that's dominated by manufacturing equipment and the telemetry that we're plugging into that to know how the machine is behaving. And that drives things like prescriptive maintenance, where you can predict when a machine might fail and predict how to avoid that or predict what to do with your workload. But it's really about the cacophony of sensors that sit around this equipment now. There's industrial sensors as well, so that's not necessarily part of the manufacturing equipment, but that might be something that sits in an oil and gas field or sits on a wire fence protecting a property somewhere and looks for vibrations or for light changes. There's autonomous vehicles. So much as autonomous vehicles on public roads is a fairly sort of minor thing now, and there's a lot of work to get us to somewhere where we're going to see a lot of that in public. In industrial and private land, autonomous vehicles are becoming more and more popular. If you go to Heathrow Airport, for example, you can jump in an autonomous little two-car bus thing that'll take you from a car park into the airport. It's totally unmanned. It has a small level of AI in it, and it drives itself. So you can call it, jump in, and away you go. That's just one example. There's trucks, there's pallet loads, there's robots that carry loads around warehouses. All of these are autonomous vehicles, and all of them are connected to the internet, or not publicly, probably, hopefully in those circumstances, but they're connected to the network to get the data to spread around. And then there's vehicle fleets. So if you have a lease car from your organization, that fleet will be connected. If you're driving delivery trucks or postal vans or whatever it may be, all of those fleets are connected data-wise. They have sensors on them that track them via GPS. There are weight sensors that track the load. There are even sensors in the cab to ensure drivers are taking rests when they need to. So all of that data is going back to a data center somewhere. So IoT is a massive coming together of an extremely diverse set of devices. So why do we care about that? So I've already mentioned about all the data that's coming back, and I've said that somebody's going to be making some money out of it somewhere. But why do we care? So the value from each device is increased when you aggregate it with value from other devices. So if you look at autonomous driving, you use the data from cars that you're getting. So you know that the data that immediately around you is being fed to you on the dashboard somehow, as well as activating the controls in some way. So braking, accelerating, and steering, hopefully. If you start moving that data from your vehicle to vehicles that are further behind you on the road, your vehicle can send data around the road conditions or the weather conditions or the traffic conditions, or things like if you're hitting potholes. And what that means is the car behind you can then take different actions depending on your experience of the traffic in front of you and then the driving conditions that you're experiencing immediately. So you're helping drivers further back. At the same time, your car could be being helped by drivers in front of you. And so it becomes a collaborative effort of all the devices aggregating their data together in order to improve the user's experience. This is all about augmenting data. If you then augment external data sources, such as the weather service, and using an API to call in with current weather conditions and predicted weather conditions for the next hour, that could impact the routing that your vehicle decides to take. So if on the GPS service, it may be that certain roads become more treacherous or certainly less safe under certain weather conditions, and so the vehicle will make a decision not to go in that direction. So that's around augmenting all of these different devices together. A device can also be a producer and a consumer of the data. So if you think of a sensor, that's usually just a producer because it doesn't need to consume anything in order to do its job. All it will do is sense whatever it's out there to do, whether it be light or vibration or noise or video. It'll make the sense, and then it'll push the data back into something that will do something with that information. But there are plenty of devices out there now that are also managed or active devices, so they also need data flowing in the other direction as well. They'll be consuming data. If you look at traffic in large metropolitan areas, for example, there are cameras there that both police forces and security agencies and traffic management systems will use to make sure that you're paying the appropriate tolls for any of the roads you're driving along. You haven't committed any offences, and if you do commit an offence, they'll snap your license plate and make sure you get the appropriate paperwork through the post. Or if, within the case of the police, if the license plate triggers an alert of some kind that the license plate is associated with a crime, then it may alert an officer to go and intercept that vehicle. Now, the cameras themselves are sending data, so they're receiving the data that they're picking up in the visual field, and they're sending it back to a data center, probably where a model is sitting. They will do the inference of that data and create actions based on it. However, what's happening more and more today is in order to optimize what that camera is doing, and so that it doesn't spend too much processing time on figuring out what the car in front of it is, if a trigger is sent for a vehicle that's wanted, for example, by the police, that license plate and that information is sent to cameras in the surrounding area so that they become primed to look for that and can react much quicker than sending data back to an inference server in a data center somewhere. So now these cameras are receiving data. They're receiving information about their priorities and about what they need to look for. So that's where they become both a producer and a consumer. And deployed devices often need management. What you don't want to have is a camera in the field that you can never update the firmware on, that you can never provide a software update to it, so that it could be a possible security flaw. You certainly don't want to have to go out and pull the camera down and push another one up in its place because you need to make those sorts of changes. So there's that kind of internet connectivity as well that allows you to manage the device, but also will provide a gap that maybe an attacker can in. We might hear a bit more about that later on. The other part is obviously you'll need to reapply authentication material. If you're using a certificate for the TLS transport, so hopefully you're using TLS to encrypt any packets coming from your devices. If you're doing that, then you need to reissue the certificates occasionally because they will expire. So you need a methodology for being able to come in and reapply that. So that's IoT. Some of that is why we care about it, because you can see some of the value from it, and some of the things are what we need to think about. So one good example is a smart city. So by a smart city, and there's lots of definitions of what this is, so I'll tell you mine, and you can probably have your own. It's a city that's driven by data. So it's a city whose inhabitants' experience of that city is driven by data and by devices that are tracking various aspects of the environment, they're tracking various aspects of traffic, and they're somehow being used to enhance that inhabitants' experience of the city. That could be lots of different things. So we're talking about video surveillance is probably the obvious one. I've just mentioned that a few times. But if you think of the current situation that we have now with the coronavirus and COVID-19, video surveillance is going to play a massive role in getting us back out and making normality, or a new version of normality, return to us. And it can do that by allowing organizations and councils and city planners to actually monitor where crowds are gathering. So we can police, for want of a better term, social distancing. We can tell when there's crowds that are getting too close together, or when the people count increases to a dangerous level. And we can take actions to prevent more people coming in. So maybe it's a shopping center, and we want to make sure that the doors are sealed when enough people are inside so that there is the possibility of social distance. So that's part of a smart city. That's one use case within a smart city. You have location-based context-aware services. That might be something like smart parking. So you're driving along, you're looking for a parking space, and the application is talking to the city's services and discovering that there's lots of traffic in a certain part of the city, and there are locations where you can go and park, even possibly reserving your slot if that's the type of system that's been set up. I won't dwell on all of these, but smart buildings is another one that's very interesting. What it does is allows a building to behave according to the environment around it. So it can do things such as sensing heat levels and temperatures outside, which is the obvious one, and therefore it can either heat or cool the building accordingly. But even sensing pollution in the environment outside, so know not to take external air in without treating it or without filtering it in some way. Whereas if the levels fall down below a certain level of pollution, then that air is fine to circulate internally and cool. And that drives energy efficiencies because there's less processing you have to do, and so a more efficient means of cleaning that air. So you can see there's a lot of different use cases in Smart City, which means we have sensors for all of these things. All of them are generating and consuming data.
So Glyn, just following up on what you said here, I think a really important point of this is there's a lot of interdependencies here as well. So you've got, if you think of IoT as being sort of foundational activities, many of these could actually be dependent on each other. And so you can have interesting sort of cascading effects and whatnot.
Absolutely. And that comes back to that kind of data aggregation point I made earlier, where there's extra value in bringing those things together. But you're right, they can turn into hard dependencies. So if one breaks, the other no longer has any value at all because there's a dependency between those data sources. That's a great point. I also see there's a question around that last slide, so I'll tackle it now. The question is, in your camera example, is there an opportunity to do that inference at the edge directly on the camera or in close proximity to the camera? Network connectivity then becomes less of a latency concern. And absolutely. So that's part of what I was saying when I talked about how the camera can be primed to look for a certain item. So that model that it has is optimized then to pick up a certain license plate or pick up a certain color vehicle, for example. So a lot of that inference does happen on the camera. But what you want to be doing as well is taking that data back to a data center somewhere, because in the data center, you can do things like trend analysis of what's detected. So you take back the inference result as well as the video data. You can use it to train new models and train new capabilities in the data center, so you have access to all the historical archives. But also, with the inference piece, you can then do trend analysis. So you know that at certain types of days, certain activities happen more. Or there's a trend where you see a certain buildup of traffic in a certain area, maybe, you know it's going to impact on other areas around the city because you have that data. So absolutely, inference on the camera is absolutely critical to get those near real-time results, as close to real-time as you can get. But you're still going to need to have that network connectivity back into the data center to make certain decisions and to augment that extra data. You don't want to have all of the crime data and all of the wanted vehicle data sat on the camera. That's not particularly secure. So you still have to have that connectivity back to query what's going on in the larger data ecosystem. Hopefully that answered the question. Go ahead, Eric. You going to talk? No? Okay. Yep. So what I want to do is compare traditional applications now and IoT applications from a data point of view. So traditional storage model, hopefully everyone can recognize this. It's when you get a LUN and you attach it to a database. So you have a single LUN which has your database stored on it, and you attach it via SAN usually to a database server. This is how most of us have grown up thinking of storage, unless you're more less old than me, let's say, in which case you may have a different view of the world. So I cut my teeth on this stuff. This is the storage I knew and loved. And this is a very simple model to manage. It's a one-to-one relationship. However, we then had users, and users wanted data, and that meant they went home directories. So we then started going into file services, and that meant you had a distributed file system that multiple users could access the same data. Made it a little bit more complicated. There was all sorts of locking and race issues involved, and I remember early days of NFS trying to fight with some of those things. But what it meant is that the small files, and it was usually small files, were then accessible by multiple people. Again, it wasn't a huge distribution. Even in an organization with thousands of users, it was very rare that one folder would be accessed by the entire organization. There were other mechanisms for using data in that way. So you typically still only had 1 to 10 maybe relationship from the data to the piece that was using it. And it was very read intensive. Items would be saved there as they were worked on, and it was usually only 1 or 2 items at a day per user folder, if you think about it. So you could have sort of thousands in a day. But it was very read intensive. It was far more read intensive than it was write intensive. IoT, on the other hand, is 1 billion devices, all reading and writing, particularly writing. It's very aggressive writes because, as I said, it's sensor data that's being pushed. But there's reads as well, so they're having to consume it as well as to deliver it. And if you think about that kind of scale against what they're doing from a file services perspective, it's suddenly a huge challenge. I mentioned the locking issues we have in things like NFS v3, just on sort of tens, hundreds, or thousands of users. When you start doing that in the millions and billions range, which when you look at the edge and the amount of devices that we're creating, that's the types of numbers you're talking about. There's a real problem about how do we take that information, how do we make sure it's sequenced properly, how do we make sure it's in order, all that kind of stuff. So it's an absolute challenge to try and deal with that level of I/O. There's another question as well, I think. To have efficient IoT devices, think Wi-Fi play a critical role to have proper synchronization with uninterrupted information. So is it Wi-Fi 5 would efficient enough to get it connected on many devices, or Wi-Fi 6 would be required to have many connected IoT devices? So it depends on how many devices you're managing versus how many devices are out there. So there's all sorts of different wireless technologies that you can use to manage it. 5 and 6 so 6 obviously adds the scalability to it, but it has its own challenges. And then there's 5G as well if you're going over radios rather than Wi-Fi in that aspect. So I wouldn't say Wi-Fi 6 was, I mean, we're managing it today on standard Wi-Fi, so and standard even 3G networks and below. So I don't think it's imperative to manage the networks in that way. Obviously, the better connectivity you get, the easier it is to manage because there's less physical devices you need to have in the way. So things like routers and switches to move the traffic around. So if you don't have to manage so many of them, but then traffic management and congestion and things can become a problem anyway. So I think it's probably too technical a question to dive into for this one. But I would say there's not a dependency on 6. You can get certain advantages from using 6 and 5G and better connectivity however you're doing it. So looking at the volume of data, we have a pipeline that all data goes through, and this is the life cycle of data, if you like. So if you think of each of these circles, imagine it's a blob of data. Now I've labeled the first one data creation, and I've since changed my mind. I would consider that more now data acquisition than data creation. And I say that for a reason, because acquisition could also mean creating. But you're getting data from somewhere else. So a sensor is acquiring the data from the environment around it, and it's then transmitting that data to something else, which acquires that data and forwards it on. So data acquisition is really bringing data into the system, be it through observation of something, be it through the sensing of something, or be it through human input maybe. So data acquisition is the first stage. What we're seeing in that space is it's more and more often machines that are creating that data than it is human beings creating that data. So if you think you're taking a lot of selfies on your cell phone and you compare yourself to the sensors in an autonomous vehicle, for example, you've got a long way to go to beat that one. The next stage is really data storage. Now, when I say data storage, this can happen in multiple places, in multiple ways. So the first thing you might want to do is persist it at the edge in some form of cache or some form of device at the edge so that we can do that edge-based inference that we were talking about a minute ago. Or even just have it locally so that we have context at the edge that other devices can use in order to be able to tune what they're doing. So I talked about the cameras being fed information, for example. We will have to do that at storage at the edge. We can build up a context that other devices can attach to and be aware of. We'll then take that storage and we'll take that data, move it along the pipeline, possibly into the data center where we'll store it again. We may do some transformation and processing to that data, and I'll get to the phases of that in a minute and talk about what that means. But we'll then store that, the outcome of that again, and possibly also putting it into archives for backup, protection, availability, or whatever else might be needed of that data. You have to be very careful when thinking of IoT data, though, of what needs to be kept versus what will just overwhelm you. You capture everything is the sort of golden rule, and then you do pre-processing and filtering before you do permanent storage, so that you cut it down to the things that you can use today or that are valuable to you today, or you at least have insight that might add some value in the future. So that's the storage, multiple places, multiple ways. We then get to data processing, and that could be as simple as the application that using that LUN, if you think about in those terms. But more often than not, it's doing something to the data so that it can carry on its path. So that could be some form of data transformation, whereby you're taking the schema of data that you've been given, so possibly from a sensor, and transforming it in some way so that it becomes normalized with other sensor data that may be in a different format at its source. This way you can bring that sensor data together and use it in one algorithm or one model. The other thing you might want to be doing is cleaning it. So when the data comes in, sensors aren't perfect, they fail, they create noise. So you may be getting zero-sum results, for example, coming through. You want to clear them out, or at least average them out so that you normalize the data stream that's coming through, so that you're not getting anomalies that are triggering alarms and triggering thresholds. You need to be a little bit cautious on that so that it is an anomaly that's falsely injected as opposed to a true event. So there needs to be some intelligence in the way you do that filtering. But data processing is not just getting the execution against the data to bring the value out, but transforming the data into something else so that it can be used in other areas. And finally, we get the data intelligence, and that's really applying the models to the data, pulling through the value of the data itself, and getting the visualization or the action taken based on what that initial capture of the data at the edge is really trying to drive. So that's the pipeline that all of the data that's coming from the edge will be going through, which is why you need to do the filtering, why you need to do the cleaning and the transformation, and why you need to store data in a reusable format so you don't have to go through all that pain again. So I talked about volumes. You can see, as I said, I've said it 3 times, and I put the last one in capital, so I must really mean this. Data can come from lots of different places. So if you think about the volume, and I drew lots of lines earlier, and I said the word billions, which always gets attention. Data can be streaming from a particular sensor or a sensor group. Okay, so you can have a continuous stream of data coming from it. That could be a CCTV camera, that could be a weather sensor, that could be a temperature sensor or a vibration sensor on a machine. On the other hand, data could be batched at regular intervals. So you can have something that caches all the data up, and when it gets to a certain point, flushes it to you. Or at a certain interval, we'll send out an aggregation of that data just to conserve bandwidth. Or it could be that the data will only get released when there's a stable connection, and the connection is intermittent. So you're going to get bursts of that data coming through as well. So you can have a device that's streaming, and you could have this burstiness sitting right next to it. Data could be event-driven. A lot of data is event-driven, whereby it will only transmit packets when a certain threshold is hit or when something actually happens to cause it. A lot of that is usually when we're doing the inference in the device, as we talked about earlier with that camera. So the camera may not be sending anything out. It may be inferring everything until a certain event happens. So until that crowd gets too big for the environment, maybe, and then you get an event out the back of it. So again, that's usually small traffic. It could be something that's like a fault has happened on a machine, for example, and suddenly a support message is sent back, which is a big bunch of logs. So you could be getting those sorts of data coming through as well. So you can't predict the size of it or even when it's going to happen because it's random event driven. So you can see the volume of the data you're going to be consuming within the storage platform, as well as the I/O pattern, are pretty random. They're not very predictable. It may be that you route everything that you know streams into one place, and you route everything you know is batch and bursty into another place, and everything that's event-driven deals with somewhere else. But at some point, you have to bring that data together. So there are mechanisms, there are ways of figuring out how you buffer all those things together and converge them at some point. But it's something you have to think about when you're planning the deployment of something that's going to consume from an IoT environment, is the nature of the traffic could be very different. It's not predictable. So take what I've just said and multiply it by that billions I mentioned earlier. That one device that could have all sorts of different traffic patterns coming from it. It could be streaming most of the time, and it could also be sending events when something happens, and it could be sending bursty events as well when a threshold gets full. So that same device could be sending all those different types of traffic patterns and multiply it by the billions. You can see that suddenly that being able to cope with those devices within a storage environment is a very challenging thing to do, because you have to really think carefully about what sort of patterns it is you expect to see in your environment and plan for those, but be able to cope with the extraneous environment that will suddenly happen. Very often data is quite small in size. You'll get small packets coming from it, possibly as a stream, but it could be incredibly frequent, unless they've been bundled into batches, in which case you'll get lots of small things in a zip file maybe. And as I said, connectivity with the source could be intermittent. It's not guaranteed to be there. So very often IoT devices are built in such a way that if they'll have an almost store and forward effect, whereby if they can transmit the packet, they'll cache as much as they can. And then when that connection comes back to life, they'll send everything they've got. I've worked with certain sporting teams that need to capture data off a device as it goes past a certain part of the event track or wherever it is they may be. And so that's a very bursty thing. It's a device that wants to send all of the time, but the connectivity is very intermittent because it's only when the device is in certain locations that it can actually do that transmission. So I talked about sort of capturing at the edge, and we'll obviously have multiple edges. You have a bunch of devices in one place, and then you have multiple locations. So you have edges all over the place that will come and get aggregated together. What you end up with is you want to be able to do different stuff with that data when it gets to the data center as well. So you're going to consume it both at the edge to the immediate inference for the reason you're capturing the data. But there's a team of data scientists that you've somehow let loose into your environment that wants to do interesting and clever things with it at rest as well. So once it's got to the data center, they want to do that trend analysis. They want to build some visualizations about how things are moving around their environment, or how cars are flowing through the city, or how power fluctuations are happening on your power grid maybe. And then there's automation as well. So based on the events that are happening back at the data center, when you start doing that analysis, actually trigger something to happen. So imagine that what we have is a factory machine that's misbehaving. So there may be an immediate inference and an immediate feedback to an operator saying this is dangerous, there's something going to happen here that could cause a fire or could cause injury to the operator. So you might get an immediate feedback, or maybe just a trend. So something may be warming up or vibrating just a little bit more every day, and that leads to wear on a component. When it gets back to the data center, we'll be doing that trend analysis on it, we'll be seeing that pattern emerge, and we'll know that there's something that might happen, so we'll make that prediction. And the action may be to then reroute all of that factory line into another line, so that if that machine needs to be taken out of service rather than fail, the goods that you're creating are rerouted properly, and you're not going to end up with a stop in production whilst you're doing it. So doing that data center to work on that data as well is very key. So I'll hand over Eric to scare you like he did me with some security pieces. Thanks, Eric.
All right. So, something a little different, but it turns out that the security and privacy implications and issues for IoT are quite significant. So let's take a look at what I would call security considerations, and it's basically what are we worrying about in the security and privacy space, if you will. All right. So as Glyn had already indicated, we're talking about billions and billions of devices here. All right, so that basically constitutes a very, very large attack surface. Lots of things that somebody who is of sort of a malicious intent can go after, and it makes sort of a defense much more challenging because of just the sheer size of this attack surface. Many of these devices are not like your PC or a server or something. They are extremely limited capabilities. Glyn made the comment about the use of TLS, and he hopes that you were using it. In point of fact, what we're finding is many IoT devices don't actually have TLS, and the significance of that is some sort of encryption capabilities. In fact, some of them aren't even able to do basic authentication kinds of things. So that that presents a serious problem. Even if it has some basic capabilities, over time, for example, TLS, we have to do updates on protocols and things of that nature. And if the crypto mechanisms become a little more computationally intensive, you may have basically outgrown what the device or devices can actually do. And so this is something where manufacturers and people who are deploying this technology, especially in the context of like smart cities and whatnot, you need to be thinking ahead as to how long is this thing going to be around? What's the useful life? So if you're putting something in the walls of your house, for example, but it's only got a realistic lifespan of 3 years, is that really a practical thing to do? IoT fits into these complex ecosystems. I think the example of smart cities, in fact, when I like to talk about IoT in of itself, I don't usually get too excited. It's when you start building up these ecosystems with lots of interdependencies. Many cases, they're not, these ecosystems aren't designed explicitly, so you don't have somebody designing it from the ground up. It sort of emerges, and we've seen this like apps on iPhones and other devices where it's like, oh, well, see, gee, I could get this map function. Well, I'll just like add that to here because that would be really handy. Well, it's not from a single source. The components are being used, no idea that it was going to be exploited in a particular way. And as such, certain assumptions may have been made that when you actually sort of get into sort of the ecosystem scenario, you might want to sort of built in some like certain security or privacy functionality. But because of the way it was put together, that wasn't even it wasn't a concern. But this is under the heading of unintended consequences that you have to sort of worry about. Adding to some of the challenges we're dealing with is definitely fragmentation of standards and regulations. I can tell you, somebody who does operate in the legal arena, and more to keep an eye on the interests from lawyers and regulators and whatnot. There's a lot of concern about IoT devices, both the security and privacy implications, and efforts around the world to try and find ways to force manufacturers to actually include core functionality that can be used to protect individuals and the data. And that's definitely a work in progress. Even the standards that are covering the security and privacy are fairly early stages of development, and in a couple of slides I'll give you some examples of things that you can look at. Obviously, the widespread deployment is a big issue. 5G is going to fundamentally change that, because essentially you're going to be able to put them just about anywhere, and so they're showing up fairly heavily in most environments where network connectivity, Wi-Fi connectivity is pretty good, but when we see things like 5G, I think we're going to see an explosion of where these devices go in. Security integration. So when you talk to CISOs and security professionals, they have in their head particular models that they're using. They've got infrastructure that's been deployed. The ever popular firewall, i.e., the concept of a perimeter, is something that that is often thought about. In the world of IoT, there is no perimeter. In fact, the perimeter might be the device. So how these devices integrate into sort of the traditional infrastructure can get fairly tricky. Safety, and I'll talk a little more about this. Again, this is an area where security and privacy in themselves are challenging, but IoT devices, they may actually cause an action to take place, like, for example, putting on brakes automatically or not putting on brakes automatically when they should. And that can actually have impacts on humans, for example, life-threatening kinds of scenarios. We'd like to think that's not the case, but that's often the situation. Cost, frankly speaking, is a huge issue from a security perspective. Adding 50 cents to the cost of an IoT device may be the make or break for the manufacturer, and so they don't. And in many cases, the manufacturers are just responding to requirements that they're getting from their customer base. And if the customer didn't explicitly require security functionality or sort of core capabilities, then the manufacturers are not going to put it in because the cost is such a big element to a lot of the IoT devices. There's a huge lack of expertise in terms of dealing with IoT devices, and then add to that the security options that you could potentially use. So lightweight crypto, for example, as opposed to some of the more traditional kinds of mechanisms. And we're not seeing a lot of progress on that right now. I mean, not only is the standard's not in very good shape, but because there's a lack of detailed information that can be leveraged, it's hard to actually build up the expertise that we're going to essentially need. Patching is a huge issue. In fact, many IoT devices don't have the ability to actually undergo any sort of updates. And it's one thing to actually patch some of the embedded software and whatnot, but in other cases, you actually have to do a wholesale replacement. There may be a fundamental flaw in a protocol or something of that nature, and we're seeing a lot of devices not only can't be patched, but even if they are patchable, there may not be any mechanism to do the necessary updates. And there's actually a professor at Georgetown University who talks about possibly the need to lobotomize IoT devices, and if you were to do that you don't lose sort of the core functionality. So you've got like a smart light bulb that you need to basically turn off the smart piece because of security issues, but you want it to still function as a light bulb. So these are areas that are being sort of probed by some of the folks in the legal community, if you will. The insecure programming goes back to the low cost. So you've got companies that are not spending huge amounts of time in the software development. Software development has historically had all kinds of issues with poor programming practices. While we see in the case of IoT, they're there, and in some cases even worse because of the low cost associated with them. And unclear liability. So if you sort of saw where I hail from, I'm a co-chair in the American Bar Association for an IoT committee. If you're a technologist, that by itself should get your attention. The lawyers are actually very interested in IoT. They see this is an area of significant potential liabilities for manufacturers, consumers of the technologies, and if even those few who might call ambulance chasers, this is an area where there's a lot of attention being given right now, and things like, so where do you get the evidence that you might need to basically pursue a particular matter? Okay. So recently we've seen a concept sort of introduced in the IoT space. It's actually sort of bled over into other areas like artificial intelligence and whatnot, but the concept is basically trustworthiness. So it's not just security, and it's not just privacy. Those are both components of it. But what we're seeing for IoT, the need to make sure safety is factored into this. So especially where you've got IoT involved with vehicles, certain kind of manufacturing lines, you don't want these devices to result in failures and issues that can cause significant harm to individuals that are close to them, or in an entire city. If a particular IoT device is like, oh no, we've got a power grid problem, shut the power grid down, kind of thing. And then resilience and reliability are a couple other areas that come up, and this is in many cases more for IoT ecosystems as opposed to maybe just a single IoT device. So what that means is you might actually have to deploy maybe multiple sensors for some sort of critical function. Or if you've got the processing piece is the critical element of it, making sure that you've got some redundancy in place to deal with that. And you're having to deal with system faults, environmental problems, a lightning strike, does that take you out? And what does it mean to be taken out? Attacks, and humans with their errors, as we always say, the human is the weak link, and so as you can see, attacks and errors can actually be introduced by humans. So these devices and these ecosystems have to basically factor in the human element of the problem, if you will. So again, when we look at the IoT, threats and impacts, it's important to keep in mind that IoT devices, they're interacting with the physical world, which if you think of many of the information technology, information communications technology, depending on your preferred flavor, there's often not that dynamic of sort of touching the physical world. IoT, in many cases, is actually doing that, and that changes up the game quite a bit. Many of these devices, it's very difficult to access them, manage them, and monitor them in ways that we traditionally manage IT. And part of that's because just the massive number of them. Part of it's because they are, they may be transmitting one way. They may not have any sort of inbound connection. So there's a lot of facets of IoT when it comes to this attribute that's make it very difficult to deal with. And then the availability, efficiency, and effectiveness of cybersecurity we're finding is definitely different on IoT devices. We can't necessarily plug them into, like Active Directory to basically make sure, some aspect of authentication is done, because it may actually be authenticating devices to devices to devices, devices to devices, and not a human in any of that. And so that machine-to-machine kind of interaction changes things up. Also, what you can collect, for example, sort of classical audit logging, where you're trying to keep an eye on what's going on, just because of the sheer number of devices, just may not be practical to do that. We see a lot of issues that come to bear. If you're really interested in and details, I'll give you some references that you want to kind of take a look at. But in the IoT space, there's a lot of concern about things like counterfeiting. There's the potential for advanced persistent threats, and definitely in the ecosystems. We've seen distributed denial of service attacks. In fact, one of the very first IoT-based ones was actually using camera systems, believe it or not, which was kind of fascinating and a bit of a wake-up call for a lot of IoT manufacturers that, here you've got these video cameras online and all of a sudden it's attacking some particular website. It wasn't that the attack was very sophisticated, it's just that there was a lot of things attacking it. The list sort of goes on. There's a lot of interesting detail in the ENISA baseline security recommendations. So if you want a little more detailed information, they've gone to the point of trying to understand the impacts. So you can see on this particular slide, there's a few that are identified as they're crucial. They've got some highs and they have some mediums. So the idea behind putting these materials together is to help manufacturers and consumers of IoT understand kind of what they're getting into, what they should be really focusing on from, in particular, a security perspective. So I mentioned some of these resources. The first couple on the left-hand side are relatively new ISO standards that are dealing with IoT. So you've got a vocabulary. So if you can imagine, it took a couple of years to actually get an ISO definition for what IoT is. It was kind of fascinating to watch, not so fun to participate in. There's a reference architecture which kind of helps understand the different kinds of flavors of IoT, which Glyn sort of talked through really quickly. There are actual documents on that going into a little more detail, because depending on the nature of the device, how it behaves and how it interacts can change significantly. There's several standards that are underway. So the 27030, 27402, 24391, these are all fairly new ISO draft standards that are being put together. The 27402 is the one that I think is probably going to be the most interesting, in that it's looking at trying to establish a core set of requirements. And it's tracking fairly closely with the NIST documents, in particular the NIST IR 8259. And these two NIST documents are available free, whereas the ISO documents are typically going to cost you some money if you want to buy them. There's a couple other documents here, and I've used a little bit of materials from ENISA and the Industrial Internet Consortium. They've got a security framework that the IAC has got a security framework that's got some very useful information. So if you're very interested, or maybe somewhat interested in security and privacy, which is a fairly big deal in the IoT space, these are some of the resources available. There are not a lot of other documents that are out there. I will tell you that a lot of regulators around the world are looking to some of these materials to try and figure out what they can essentially put in regulations to try and force manufacturers to do certain things and encourage consumers of IoT to basically use. So I think with that, Glyn, I will turn it back to you. Talk about end-to-end flow.
Perfect, thank you. So if anyone wants to still do IoT after all, everything Eric just said, we'll just sum up very quickly around what that data path looks like. So what you can see here, hopefully your screen is a bit bigger than mine and you can read some of these words. What you're seeing here is really basically what I described earlier in that kind of 4 circles that we saw. It's the flow of data through an organization from the edge where it's collected at IoT and how it impacts on the rest of the data ecosystem within your environment. So you can see that when you acquire the data, there'll be some kind of data flow management. That's the filtering I talked about. That's the ability to do that pre-processing and making sure you're capturing the right data in a correct format to actually make an impact on something. You then have that stream analytics, and that's the edge processing, which could be inference on the device itself. It could be inference on an edge device located near where the sensors are. It could be some kind of cloud processing. So the first thing that gets captured is to a cloud storage unit, maybe. And that's really that kind of edge piece of analytics. You then go into the kind of data lake and data archive piece, which is where you have more static data that gets flowed into, if you like. So you have the waterfalls of data coming from the edge, filling that pool in the center up. Against that, we really have the three different applications against this. We have the batch analytics. That could be traditional analytics as well. So that could be back to the Hadoop ecosystem. Maybe you're still doing MapReduce against these things. But there's a lot of traditional applications and traditional analytics that shouldn't be forgotten. Everyone talks around AI and ML these days. There's a bunch of useful analytics that don't involve any of those things that we are still doing and doing a lot. You then move through, and there's the high data throughput pieces, which drive things like AI, ML, and deep learning as well. So ML being machine learning and deep learning. And then there's HPC for doing simulation against these things as well. So as you're capturing maybe sensor and telemetry data from an oil field, for example, you're going to want to be simulating that so you can see how the field is going to behave under different conditions and whether you think you're going to be able to get a good gas yield from that field, for example. So you can see how the data flows from a functional perspective now. Let me build it up. There we go. Oh, sorry. I advanced a little too far. What we do have, and I will just slide out again before I wrap up, you can see how we have now from what type of data stores exist in each of these areas. So on the left-hand side, we really have the edge data being captured and then going through the edge analytics, as we saw. But then you go into the middle and you start having those cloud-based analytics where you have streaming, batch, and model building all coming together in one space. Plugging into that from the bottom, you have the core data lake, and then out to the edge, you end up having that kind of HPC and AI workload. So IoT is driving all of this kind of ecosystem. You need this kind of compute power to drive value out of the volume of storage you're getting from IoT. So that was really where I wanted to end it. Just to kind of sum up, and I think we might have some questions in the chat, which I'll go back to Alex for. Internet of Things is all about data from the edge. And to me, the edge is where your technology meets your customers or your suppliers or your operators or your people. So it's where the edge of your business hits the rest of the world. It's usually devices that are generating that data, and it's usually device-to-device communication. It's not necessarily coming from people. A very small minority these days is actually human-generated and coming from a person itself. It's complex and it's unpredictable data patterns. You need to be able to manage burst. You need to be able to manage high streams and high throughput. You need to be able to manage event-driven traffic. So it's unpredictable, and you need to be able to build that into your ecosystem to be able to cope with it. Capturing the data isn't enough. It's no good getting all of this data from the sensors, getting it into a static place and going, I've won, I've done it, because you need to be able to drive that information. The data is going to be used in many different ways, not just for the reason it's been captured, but for trend analysis, for further aggregation with other data sets to drive more value. You have to be able to use that data in multiple places, which means you need an ecosystem whereby you can pull that data out and apply it to other workloads. Security and governance needs to be information and context sensitive. As you're capturing this data at the edge, particularly if it's about a person, and this is dependent on the geographies you're in as well, as you're capturing that data, the data has a long way to go through all of those boxes that I went backwards and forwards through a couple of slides ago. The security and the governance of that piece of information needs to travel with it. So wherever it lands in any of that ecosystem, in any of that architecture, the context of how you need to protect that data, who the data belongs to, and what it can be used for travels with it. It's not device-centric security anymore, it's information-centric. And IoT is no good in isolation. You have to have that whole pipeline to be able to bring the value, to be able to leverage that data to train new models and then redeploy out to the edge again with those new models to drive new data as well. So I'll hand back to Alex to clean up. Thanks.
Thank you very much, Glyn. And thank you very much, Eric. That was very edifying. It was really interesting. Thank you. There is one further question from the audience I'll address really quickly. Is there any collaboration between IoT efforts at SNEA and another SNEA initiative around computational storage? Many IoT devices include some form of storage already, and the idea of localized processing where the data is created and stored may help solve some of the latency and security challenges. The answer is, in any given Venn diagram of IoT and computational storage, there's going to be a high degree of overlap between those two circles. The answer is yes, there's going to be work done in this area. I don't think we'll deliberately call it IoT, but I think we'll be sensitive in fact that we are developing new technologies that require a common approach in a lot of respects. So thank you very much for your attendance today. The feedback is really important to us. Please rate us as you leave. There's a copy of the slides. You could either get it right now or you can get it later from our educational library. And we're going to post a Q&A where the questions that were asked today will be posted up and answered in a written form. You can also follow us on SNEA Cloud. But in the meanwhile, thank you very much for your attendance. Thank you both to Glyn and Eric for their presentation, and I hope to speak to you again shortly. Thank you and good day.